Okay. So I mentioned today we want to talk about some applications of integrals. And on Friday we'll actually learn another integration technique. But right now, some real-world problems we can apply these guys to. One we've already seen. These are the motion applications. That's basically when you have position, velocity, acceleration, jerk, etc. You understand that we can travel through these kinds of functions using differentiation if we're moving in one order. But if we have information down here, we want to recover information from up there, integration helps us with the other order. So there was that. We saw that already, and we already did an example of that. Something closely related to this, though, would be displacement. This will, again, very closely related here. Displacement is talking about one of our motivating examples where we kind of realize that the area under the velocity graph could tell us about the distance traveled. To displacement is specifically, though, the distance traveled from some reference point. Right? So when you talk about the distance from a reference point, you call this displacement. So let's say you can you start here. You travel 5 meters in that direction, you turn around and you travel 4 meters in the opposite direction, and then you end here, then we can say your displacement is 1 meter, right? Because the distance you end up from your original position is 1. However, the total distance you traveled is actually 9 meters, right? You travel 9 meters in total, but if we take into account how far are you from where you started, the answer is 1. Okay, so that's the difference between displacement and distance traveled. And we can talk about both of these in terms of integrals. And the argument is kind of the same. This leads to the following definitions: displacement on, say, some time interval AB, that will be given by the integral from A to B of the velocity function. Okay, so this is basically, if you count from t equals A, which is some initial time, to t equals B, and you want to find displacement, it is simply an integral. Right? Now that will tell you the actual distance you move from the original. Now velocity usually has some sort of mechanism for indicating direction. In one dimension, it's literally just by a sign change. So someone can define, okay, when we're moving to the right, we'll consider this positive velocity is the speed at which we move to the right. The speed at which we move to the left, we'll consider negative velocity. And so the displacement is computed by adding 5 and then subtracting 4, which leaves you with 1. And this will account for that. You'll notice that whenever your velocity is negative, your graph goes underneath the x-axis. It'll compute the area as negative area. So it's talking about distance you're reversing versus distance you're going forward. This will actually take everything into account in terms of where you started. However, if you wanted to figure out what distance was traveled, well, you'd have to take the 5 and then you'd have to add the 4. But your 4 is negative, and so technically how you can think of this is as 5 minus the negative 4. You subtract the negative to make it positive, and of course we know how to do that. That's absolute value. That's exactly what the absolute value function would do. And so that gives us total distance traveled. on an interval, some time interval, is actually look at the magnitude of the velocity. So don't compute any negative areas, add up all the areas and tell us about the distance. And that leads us to this application. And so these two are on the bonus problems on the quiz today. So that's the difference. If we just integrate velocity, we get, technically speaking, what we call displacement. However, if we take the absolute value, we get the total distance traveled. Let's look at an example here. Again, I don't really care about the units, it could be t seconds, minutes, whatever. But we know the velocity function is given by, say, t squared minus 16 plus 5. I want you to find a the displacement from t equals 0 to t equals 3, let's say. Okay, so from time equals 0 to time equals 3, what is the displacement experienced by the particle? And 2, what is the total distance traveled by the particle? So I had here, when is the particle moving? Forwards, backwards. It's a word problem. So A should be able to start here. We're looking for displacement. This is simply given by the integral of the velocity function on the interval of consideration. So this is going to be integral from 0 to 3, and then just integrate the velocity function. Not tough here, it's just an application of the power rule on 0 to 3. Plug in 3 here, we get 9 minus 27 plus 50. And 9 plus 15 is 24, so it gives us minus 3. In other words, you end up 3 units behind where you started at the end of this trip. At B, well, total distance traveled. Well, this will just be the integral from 0 to 3 of the absolute value of the velocity. Of course, remember absolute value, how that would work. Means we're going to integrate the velocity function whenever the velocity is positive. We'll integrate the negative of the velocity function when the velocity is negative. How do you figure out where a function is positive versus negative? What would you do? What's the first step here? If I give you a function and say, where is it positive, where is it negative, what would you do? Yeah? Well, that's not the same as asking where it's maximum or minimum.
Well, I was thinking like increasing.
No, increasing, decreasing has nothing to be positive or negative. You can be below the x-axis and increasing. So that has nothing to do with it. Yeah?
On the derivative
Why?
for the slope or down the line.
What does it mean to be positive? So I'm asking, what does it mean to be positive? What is positive? I don't know the meaning of that word. What does it mean? Yeah?
If the y value is positive or negative.
Yeah, what does that mean to be
So it's
positive?
just like above x-axis or below.
Okay, you're above or below. How do you know if you're above or below?
By plugging in point. No.
Okay, I plug in a point. How do I know if it's above or below the x-axis?
If it's positive, it would be above. If it's
What does it mean to be positive? Yeah?
greater than 0.
You get a number that's bigger than 0, a number that doesn't have a negative sign in front of it. So there's the horizontal, which is where t equals 0. You want to know when is the graph on top, which means it gives you a value that's greater than that, where v equals 0. Where it gives you a value that's greater than that, and you want a negative would mean it gives you a value that's below that. So here's positive, and here's negative. And notice that you're talking about positions. You're talking about what side of 0 you're on. It's a position, which means you would not look at the derivative. Derivative does not tell you about position. Derivative tells you about speed and slope, and velocity. So you want to know about a position regards to the 0. So what you would do is you would set the function equal to 0, and then test the intervals. That's how you find it. Okay. It has nothing to do with derivative, because positive or negative is a positional thing. Are you on the right side of 0, or are you on the left side of 0? What position are you in? So I'd set the original to equal to 0, and I would solve. Does this factor?
Yeah.
5 and 1. So it means at t equals 5 or t equals 1, our velocity is actually 0, which would mean I can actually just test the intervals now and figure out where is it. I know where it is 0. So at 1 and 5, it's actually equal to 0. So I plug in a random number over here, like I plug in t equals 0. Here I would get a positive number. And plug in a number in between here, like 2, I would get a negative times a positive, that gives me a negative number. Plug in a number over here, like 6, and that will give me a positive number. So here is where it's positive, here is where it's negative, in terms of positions. And by the way, that also tells me, at this point I can answer C right away. I know it's moving forwards for t in 0, 1, and it's moving backwards for t in 1, 5. Okay. But more importantly, I know it hits 0 at 1, it's above the horizontal before 1, and it's below the horizontal after 1. But so now to just actually get back to B. So this guy, how I'd actually compute that guy, is I'm going to integrate from 0 to 1, I'm going to integrate the velocity function, and then I'm going to subtract what I get, integrating it from 1 to 3. So this will actually give me a negative area, which is the negative distance covered, that period I'm moving backwards. I take its negative to talk about the positive distance traveled over that time, and here it actually traveled a positive distance already. Yeah?
In order to get the position function, like you're looking at Barbie's using velocity.
Okay.
So for the line, we are testing the position of the point.
I want the absolute value of velocity. This function is defined in terms of where your function is bigger than 0 or less than 0. So I find where it is 0, then I can find where it's bigger than 0 or less than 0. And that's going to tell me how I want to actually break up this interval. So between 0 and 1, this is the positive part, and between 1 and 3, that's the negative part. Of course, we kind of knew that. I mean, this is a parabola after all, so we did know. But of course, in general, we couldn't really know that. But yeah, this is just a quadratic. I know it's going to be negative in the middle because it's opening up. But ultimately, this is going to be the computation needed to find the total distance traveled. And so it's pretty much going to be that same guy, t cubed over 3 minus 3t squared plus 5t. But this is evaluated between 0 and 1 minus t cubed over 3 minus 3t squared plus 5t. That's evaluated between 1 and 3. So if I plug in 1, I would get a third minus 3 plus 5 minus, if I plug in 3. We actually computed what this was when I plugged in 3 already. That was actually minus 3, as I recall. And then minus what I get when I plug in 1, which is going to be the same thing, 1/3 minus 3 plus 5. So that's ultimately going to be what it looks like. Minus this is going to be doubling that, so this is 2/3 minus 6 plus 10 minus plus 3. So this is 13 minus 6, that's 7. So it's 7 and 2/3. 7 is 21 over 3 plus 2 and 0 over 3 is the total distance traveled. So this thing started at some point. It traveled some distance and then traveled to 3 units behind where it was. So this distance is 3 units. But the total distance traveled was 7 and 2/3 units. And to finish part C, max and min volume for max or min velocity. Here's where I need the critical points because the derivative tells me about maximums and minimums. So find v prime. What was the original v? I already said it was t squared minus 5 minus 6t plus 5. Right, so that's going to be 2t minus 6. I'm going to set that equal to 0. Or undefined. It's never undefined, so this means t equals 3 is where the critical point happens. Okay. Now, you can test that critical point in the derivative. If we plug in a number over here like 0, I get it's negative. Plug in a number over here like 4, I would get it's positive. So it's decreasing here, increasing there, so this is where the minimum occurs. So we have min velocity at t equals 3. That's when it's moving the slowest it could possibly move. In terms of even backward speeds. In terms of the maximum velocity, requires that we look for the absolute max because there's no local max to speak of here. You would also notice that you can recall that our graph looks like this. It'll actually hit, this is where t equals 3. We're considering the interval between 0 to 5 as I recall. And so I would test the endpoints. V of 0 and V of 5. V of 0 5. V of 5 would be 25 minus 30 plus 5. That would be 0. So here's our max velocity. So it's actually moving at its fastest from the very beginning. It shoots off. So C was kind of a recap. The new applications I told you about was displacement and total distance travel. And that's how you deal with them. So that's 2 applications. Here's a third application. To find the average value of a function. And by average value, I mean the mean average. There are many ways to compute averages. The mean is a very popular one. Of course, you remember how to do this from basic statistics class. Given a finite number of numbers, x1, x2, all the way up to xn, the mean of these values, often called x bar, is just you add up all the numbers, and then you divide by the number of numbers there are, right? That's how you find the mean average. Now, here's the question. Given a continuous integrable, and you'll see why we need an integrable function f on AB. So here I have my function on some interval a, b. Now what I care about is finding what is the average output of this function. So for every single point on this function, right? If I were to look at the y values, right? And so I'll get these numbers here. If I were to add up all of those numbers and divide by the number of numbers there are, what would I get? Okay. Now, obviously there's a challenge here because there's an infinite number of points, right? It's a continuous function. There are no gaps in this function. So I need to know, how would I add up a continuous number of points? What would be the average output of this function on this interval, right? So now we have to figure out a way to add up an infinite number of things and divide by infinity. What does that even mean? Well, we have a mechanism by which we can add up an infinite number of things. It's called the integral. That's pretty much one of the nice, what do we call it, collateral benefits. You know, we started out talking about derivatives because we wanted to solve the rate problem. Let's figure out how fast this thing is moving. But we've got a lot of side benefits to doing that. You know, we could apply it to optimization, related rates, all sorts of problems. One nice computational advantage we got from the derivative was linear approximation. It allows us to approximate functions that are complicated by using straight lines or planes, as you'll see in multivariable calc. One of the nice side computational benefits of the integral, figuring out how much space something takes up, is that we're now really good at adding a lot of things. By that I mean an infinite number of things. If you're in a situation where you want to add up an infinite number of things, odds are there's going to be an integral in there somewhere. Especially if you're adding up some sort of continuous function. And you actually don't have to go that far in math before you encounter this. Even in a basic statistics course, you'll come up with something like a continuous probability distribution, like a normal distribution. And you might want to know, what is the average of this random distribution that I'm looking at, right? So you might have a situation where you have a function outputting an infinite number of values where there are no gaps, there are no holes, but you want to find an average. How would you go about doing that in general? Okay, so the example of the normal distribution is a special example. We actually know how to find the mean of that very nicely. But given a random function, what is the average output? Okay? So you might also recall we looked at a situation where we could dissect an interval into a bunch of pieces, n pieces, and we could figure out the interval of those, the length of each of these pieces, And we could say we derive that delta x from b minus a over n, where this was the a and b were the endpoints of the interval. This means that I could actually set n to be b minus a over delta x. How is that helpful? Well, here's how it's helpful. Suppose you want to find the average of n output values of this function, right? So I have a list of outputs, f of x1, f of x2, etc., all the way up to f of xn. Find the average. Well, we'd simply use this formula. The average output is going to be me adding up all these numbers and dividing by the number of numbers there are. Well, it turns out I can write n in this way. This will over delta x. I can flip and multiply, so this will give me f of x1 plus da da da, f of xn, all of that times delta x, all over b minus a. This is of the n values. What if you want to talk about all the values? Well, let n go to infinity. So the average value, this is of all values, of all outputs. Well, let the number of points I'm selecting go off to infinity. Now, b minus a would just be a constant with respect to n. I can factor that out. A nice way to write this is by a sigma notation. And that, by definition, is the definite integral. The average output of a function on an interval is given by this equation. I can add up an infinite number of values and find their mean average via integration in that way. So I can ask you about what is the average value of a function on an interval? This is how we compute it. So if it were possible for me to gather all of the y values, and I can add all of them, and then divide by the number of y values there are, what number I would get is this number. Here's an example. Find the average value of x squared on 0, 2. So we do know y equals x squared looks like this. We're looking at 0, 2. I only care about this part of the function. Now I know the smallest value outputs is 0, the largest value outputs is 4, but it actually outputs a bunch of values in between those. It outputs an infinite number of values in between those. So if I were to gather all these y values and find their average, what would I get? Well, I have a formula for that. The average is going to actually be equal to 1 over b minus a times the integral from a to b of the function. So this is going to be a half the integral from 0 to 2 of x squared. This will be 1/2 times x cubed over 3 between 0 to 2. This will be 8 over 6, which will be 4 over 3. Turns out the average output of x squared on that interval is 4/3. So if I were to add up all these values, divide them by the number of values there are, 4/3 would be the answer. Since we're here, there's something else I can tell you about. There's also a mean value theorem for integrals. Suppose f is continuous on AB and integrable there. Then there exists some C in AB such that that output is equal to your average output. This is called the mean value theorem for integrals. There is a point on your function, so the point 4/3 is somewhere here. There's definitely some input value that when I plug into your function, call it C, it gives me 4/3 as the output. And this would have to be the case. If all outputs were below the average, then the average would be lower. If all outputs were above the average would be higher, right? So there must be someone at the average. Let's do it for the same function. Another example here. So we've got 4/3 as the answer. This means we want C in 0, 2 such that f of C gives us the average output. This means your C squared must give you 4/3. This would mean your C would give you the square root of 4/3 plus or minus. So this is 2 over radical 3. And of course, since we want to be in 0, 2, I would take the positive value. So that input will give me the average output. So, some nice applications there. One more application I want to talk about. Application number 4. This is kind of an important one for traditional poetic reasons. Finding the error between curves. Now, this is useful in several contexts, but we like it because this is actually the full solution to the error problem. might recall how the area problem started. We had a blob that we wanted to find the area. Thanks to Fermat, we have analytic geometry. No, not Fermat, Descartes. We have analytic geometry, invented the xy plane. We put this on an xy plane, and we want to look at it as a function on which we can do calculus. However, it failed the vertical line test, so it's not a function. So what we did instead was, okay, let's solve half the problem. Let's worry about the top part of the function. Okay? Can we find the area under this curve? And then we had that idea about slicing it up, creating rectangles, using these rectangles to approximate the area, taking this approximation to infinity, and we end up with the integral. Now it turns out we could do the same maneuver with the bottom. Okay? And we could do that here and find that area. However, now if you want to kind of put all these ideas together, what you can realize is, if I want to find how much space this thing takes up in general, it's just a matter of finding the area between the green curve and the red curve. I can express the problem as that idea. Once I can find the area under one curve, just apply the idea on both ends at the same time, and I can find the area between curves. Finding the area between the curves helps me find the area of whatever object I'm looking at, once I kind of fix it nicely on the x-axis, xy plane. So, how would you actually go about doing that? Well, here's the idea. Consider two functions f of g on AB such that, let's suppose that the f is always larger than g on this interval. So I have my f doing its thing, and I have my g doing its thing. This is your f, this is your g, this is your a, this is your b. And I'm interested in finding the area between these two curves. So I can call that A. So that's A. Now, in light of what we've done before, how could we actually compute this guy? Well, I'll show you. Here's my F. Here's my G. Here's my F. Here's my G. That's F, that's G. That's F, that's G. That's A. That's B. That's A. That's B. Here's how we can get to that area. What we can do is first find the area under F. Okay. That I can compute by taking the integral from A to B of f of x. Then I can find the area under G. And I can compute that by taking the integral from A to B of g of x. Now, if I take this area and I subtract this area, so I take away the area under the bottom, I would end up with the area on the top. So take this minus that, and that will give me what the area is. So the area can be equal to this minus that. Now, via our properties of integrals, I can rewrite this. Integrals distribute across sums, so I can actually write this as one big integral, where I'm subtracting the top function from the bottom function, and I'm integrating that result. And in fact, probably the way you want to remember it is exactly like that. If you want to find the area between curves, it will be the integral of the top function minus the bottom function. dx. And that's probably how I want you to remember the formula. You will start to get a little bit of this in Calc 2, but once you get to multivariable calc, it's going to be super important for spatial awareness. So thinking of things in terms of who's on top, who's on bottom, who's at the right, who's at the left, something you kind of want to, that's a habit you kind of want to get into. So rather than memorizing some generic formula, memorizing things in terms of their positional relation to each other is a pretty useful tip for cases where spatial awareness is going to be key, which in Calc 3 it is, because you're working in 3D and it's going to matter where guys are. You have a question?
Top function is always the greater one?
Yes, the top function by definition is the one that has the largest y values. And you should note that this role can change on a given interval, which the examples that we're going to do will show that situation. But this is ultimately how you find the error between two curves. Figure out who has the largest y values, who has the smallest. Bigger guy minus the smallest guy, integrate. That gives you the area. Here are some examples. Here's a situation. This one comes to you in a picture, because I kind of just want you to interpret things here. So you have one function doing this. Call that one f of x. And you have another function that's just like a straight line cutting across here. Call that one g of x. They intersect here, here, and here, and call this first intersection point A, B, and C. And the bounded region is going to be this. Describe how you'd find the area, write down a formula to compute the area. And you'll do that for next time. We'll do these next time and move on to another integration technique. Should be a lot of fun.